Welcome to this explainer. Today we are taking a truly fascinating, photorealistic cinematic journey right through the heart of a modern outdoor distribution substation. If you've ever driven past one of those fenced-in grids, the ones with all the buzzing metal and ceramic, and wondered, what exactly is going on in there? Well, you are absolutely in the right place. We're going to track the exact step-by-step journey of an electron from the literal second it enters the facility as high-voltage transmission power to the moment it leaves, totally tamed and ready to power our neighborhoods. Okay, let's dive right into this. What we have here is our complete roadmap. It's a 1 to 10 sequential path that electricity follows through the entire substation. Every single component standing in this yard has a highly specific job, whether that's to protect, measure, or transform the power. So we're going to follow this exact sequence, step by step, starting from the incoming line way over on the far left, all the way across to the outgoing feeder on the right. To make sense of it all, we can break this journey down into 5 main zones. Number 1, arrival. Number 2, first defense and measurement. Number 3, fault protection and isolation. Number 4, the heart of the substation. And finally, number 5, delivering outgoing power. So let's kick things off with section 1, arrival. I want you to literally imagine you are the electrical current itself, just surging down the upstream distribution line and arriving at the front gate. This right here is component 1, the incoming feeder. Depending on the specific scale of the substation, you're rolling in with a massive amount of potential energy. We're talking usually 11 kilovolts, 33 kilovolts, or sometimes even up to 132 kilovolts. This is the grand handoff point from the broader transmission network directly into our localized distribution facility. Moving right along to section 2, first defense and measurement. The electricity doesn't just get to flow freely once it's inside the gate. No way. It faces a rapid-fire 3-step sequence basically the second it enters. First, we arrest any dangerous surges. Second, we measure the current. And third, we measure the voltage. Doing this ensures the power is safe for all the equipment ahead and absolutely crucially that it's completely measurable for the grid operators watching the whole system. Think of component 2, the lightning arrestor, as the heavy-set bouncer at the club door. Its entire job in life is to protect the downstream equipment from massive overvoltage. Say a lightning strike hits the line a few miles away, or there's a huge switching surge somewhere on the grid. This arrestor catches it, and because it's connected directly between the power line and the earth, it safely and instantly shunts those insanely dangerous surges straight into the ground before they can, well, blow up the rest of the substation. And this brilliantly illustrates our next 2 stops, components 3 and 4. Once we've cleared the bouncer, we hit the security cameras. These are the CT, which stands for current transformer, and the PT, the potential transformer. See, the raw current and voltage coming in are just way too high to measure directly. It completely fries standard equipment. So these devices step them down to safe standard values for the metering and protection relays. The CT sits in series with the line and steps that massive high current down to a tiny 1 or 5 amps. Right next door, the PT is connected in parallel with the line, stepping the extreme voltage down to a super manageable 100 or 110 volts. They work together to constantly accurately monitor the exact flow of power. Now for section 3, fault protection and isolation. Meet component 5, the circuit breaker. This is the main protection device of the entire setup, hands down. If those CT and PT security cameras we just talked about detect a serious fault, like a massive short circuit, they immediately signal this breaker. Acting kind of like a heavy automatic vault door, the circuit breaker violently and instantly slams open. It interrupts the fault current even while under a heavy load, totally isolating the faulty section to prevent a catastrophic meltdown. Actually, if you've ever had your house lights flicker and go out during a crazy thunderstorm, you've probably felt the immediate downstream effect of one of these breakers slamming shut to protect the larger grid. Now, there is a really critical difference between the circuit breaker we just saw and component 6, the isolator, sometimes called a disconnector. While the circuit breaker is designed to literally blast open automatically while massive power is actively flowing, the isolator, well, it's strictly a manual safety device. It provides a physical, visible break in the circuit so maintenance crews know for an absolute 100% fact that the line is safe to touch. The golden rule here is that the isolator is only ever opened after the circuit breaker has completely de-energized the equipment. Okay, moving into section 4, the heart of the substation. Right here, we are talking about a massive, massive reduction in pressure, basically taking a highly dangerous 11 kilovolts of electricity and stepping it all the way down to a highly usable 0.415 kilovolts. And all of this heavy lifting It's done by component 7, the power transformer. This thing is the undeniable workhorse of the substation. It takes that raw, high primary voltage that just traveled across the region and steps it down to localized distribution levels. The sheer size and scale of this transformer are totally dictated by its required capacity, which is measured in kVA or MVA. That basically tells us exactly how many homes and businesses it can support. It literally transforms dangerous transmission power into the usable, everyday distribution power that eventually reaches your street. Finally, Section 5, delivering outgoing power. As we map out the final 3 steps, components 8, 9, and 10, on the outgoing side of the facility, you'll notice the sequence mirrors some of the safety features we saw right at the beginning. We need to isolate outgoing faults, provide a visible break for maintenance, and finally, feed the distribution network. So, component 8 is the sectionalizer. This can be a recloser or a load break switch, and its job is just incredible smart grid management. Imagine a tree branch falls on a power line down your street. Well, this sectionalizer automatically isolates that specific faulted section of the network on the outgoing side. By doing this, it completely prevents a localized neighborhood issue from taking down the entire substation. It keeps the power flowing to all the healthy parts of the system. Pretty smart, right? Now, we already saw component 6, which was the incoming isolator right before the transformer. But notice here we have component 9, a second isolator or disconnector located just after the sectionalizer on the outgoing side. You might be wondering, why do we need 2? Well, just like the first one allowed for safe, visible maintenance of the main substation equipment, this outgoing isolator does the exact same thing on the back end. It provides that crucial, visible isolation to ensure safe maintenance of the outgoing feeder lines or any specific outgoing equipment. And that brings us to component 10, the outgoing feeder. This is it, the final departure point. The electricity, having survived its crazy gauntlet of measurement, protection, and transformation, now flows out through overhead lines or underground cables directly into the local distribution network to supply everyday consumers. Now, before we wrap up today, I have to point out one invisible hero sitting literally right beneath our feet. Underneath all 10 of the components we just toured is the earthing system. Every single equipment frame and all the neutral points are solidly earthed directly into the ground. This foundational grid is absolutely vital. It ensures personnel safety, protects the highly sensitive equipment we just looked at, and guarantees the proper operation of the entire system by giving any rogue electricity a completely safe path to zero potential. So the real takeaway here is this. Electricity doesn't just magically appear at your house. It runs an incredibly complex, highly sequenced 10-step obstacle course of physics and engineering designed purely for your safety and reliability. So the next time you flip a light switch, will you picture this incredible gauntlet of protection and transformation those electrons just survived inside that fenced-in grid down the road? I really hope you do. Thank you so much for joining me on this explainer. I hope it sparked a totally new appreciation for the hidden infrastructure powering our daily lives. Keep learning, and I'll catch you next time.